My dear children, once again welcome to your physics class. Hope you all are fine over there. Children, in the previous session we had discussed about thermal expansion, different types of thermal expansion. Also we derived the relationship between the coefficients of thermal expansions. And we got a result, that is the coefficient of linear expansion is, or the coefficient of area expansion is 2 times coefficient of linear expansion. Similarly, the coefficient of volume expansion is 3 times coefficient of linear expansion. Okay, so today let's discuss about an important concept of this chapter, that is anomalous behavior of water. Along with that, we will discuss several concepts of this chapter. So let's get started. So first we are going to discuss anomalous behavior of water. Anomalous means an abnormality, an abnormal behavior of water. So you know that generally volume of the liquid increases with temperature, isn't it? When we heat the liquid, its volume also increases. But when water is heated, what happens? Its volume decreases. Children, please listen. Whenever generally volume of the liquid increases with temperature, but in the case of water, when it is heated, its volume starts to decrease from 0 degrees Celsius and reaches a minimum at 4 degrees Celsius. That means when the temperature increases from 0 to 4 degrees Celsius, its volume decreases. The volume of water decreases and reaches a minimum at 4 degrees Celsius. And where the volume is minimum, there the density will be maximum, because density is mass by volume. So when volume is minimum, density will be maximum. Hence density of water is maximum at 4 degrees Celsius. So this is anomalous behavior of water or abnormal behavior of water. Generally volume of the liquids increases with respect to temperature, but in the case of water there is an exception. In the case of water, when the temperature increases, its volume decreases, and finally when the temperature reaches 4 degrees Celsius, its volume reaches minimum and its density becomes maximum at 4 degrees Celsius. So when the density of, or at which temperature density of water is maximum? At 4 degrees Celsius. So let's go through the screen. So here you can see water shows some exceptional behavior, that is when it is heated at 0 degrees Celsius. It contracts instead of expanding. That means when it contracts, its volume decreases. So it contracts instead of expanding, and it happens till it reaches 4 degrees Celsius. The volume of given amount of water is minimum at 4 degrees Celsius. Therefore, its density is maximum. So refer the figure. Figure is there in the next slide. We can go through the figure later. After 4 degrees Celsius, what happens? After 4 degrees Celsius, water starts expanding. Okay, so till 4 degrees Celsius, volume of the water decreases, that is it contracts. After 4 degrees Celsius, water starts expanding, that means its volume starts to increase. So below 4 degrees Celsius, the volume increases and therefore the density decreases. This means the water has maximum density. Children, it is not below 4 degrees Celsius, it is above 4 degrees Celsius. Okay. This is above. So above 4 degrees Celsius, the volume increases and therefore the density decreases. This means water has maximum density at 4 degrees Celsius. Now, what is the advantage of this anomalous behavior of water? See, because of this property of water, in lakes and ponds freeze only at the top layer and at the bottom it does not. But if the water freezes at the bottom also, then animal and plant life would not be possible, isn't it? So due to this anomalous behavior of water, what happens? The water in the lakes and ponds freeze only on the top layer of the surface, okay, on the top layer of this water resource. So only freezing occurs at the top layer. At the same time, freezing doesn't occur at the bottom layer. So what happens? Yeah, animal and plant life would can survive in the bottom, because if water freezes at the bottom, then the animal and plant life would not be possible. So this is the advantage of anomalous behavior of water. See, this is the diagram. So this shows the anomalous behavior of water. So here you can see, when the temperature increases, the volume of the water decreases. See here, the volume of the water is decreasing, and this is 4 degrees Celsius temperature. At 4 degrees Celsius, the volume becomes minimum, and after 4 degrees Celsius, the volume starts to increase as shown here. So when the volume starts to increase, the density decreases. Okay, so this is the anomalous behavior of water, and this graph clearly shows the anomalous behavior of water. Next, let's discuss about heat capacity. So what do you mean by heat capacity? The change in temperature of a substance when a given quantity of heat is absorbed or rejected by a substance is characterized by a quantity called the heat capacity of that substance. And heat capacity is denoted by S, and the equation to find out heat capacity is delta Q by delta T, where delta Q is the heat energy absorbed or rejected, and delta T is the temperature change. Okay, so whenever the object absorbs heat, or whenever an object rejects heat, there is a change in the temperature of that substance, isn't it? So whenever the object absorbs heat, temperature of the object increases. Whenever the object rejects heat, temperature of the object decreases. So this change in temperature of the substance is characterized by a quantity called heat capacity. It is denoted by S, and the formula to find out heat capacity is S is equal to delta Q by delta T. And we can define heat capacity like this. Heat capacity is the quantity of heat required to increase the temperature of whole substance. So what is heat capacity? It is the quantity or amount of heat required to increase the temperature of whole substance. To increase the temperature of a substance, how much heat energy is required? That quantity of heat is the heat capacity. Okay. Next, what is this specific heat capacity? That is also closely related with heat capacity. So specific means we are specifying some values here. So while defining heat capacity, we simply defined it is the amount of heat required to increase the temperature of whole substance. But here we want to specify the mass of the substance. So we can say every substance has a unique value for the amount of heat absorbed or rejected to change the temperature of unit mass of it by 1 unit. So this quantity is referred to as specific heat capacity of the substance, and we can define specific heat capacity simply like this. It is the amount of heat required to increase the temperature of unit mass of substance by 1 unit. Okay, so what is specific heat capacity? It is the amount of heat required to increase the temperature of 1 kilogram or 1 gram. That means required to increase the temperature of unit mass of substance by 1 unit. So to be more specific, the equation for specific heat capacity can be written like this. Specific heat capacity is denoted by small s. Okay, it is denoted by small s. So the equation to find out specific heat capacity can be easily obtained from the equation for heat capacity. So this is the expression for heat capacity, and that is delta Q by delta T, and specific heat capacity is denoted by small s, and that will be equal to capital S by small m, where m is the mass, because we know here we need to specify the mass. So specific heat capacity is S is delta Q by delta T and divided by M. So this will be the expression for specific heat capacity 1 by M into delta Q by delta T, where M is the mass and delta Q is the heat, delta T is the change in temperature. Okay, so this is the expression to find out specific heat capacity, and the SI unit of specific heat capacity is joule, kilogram raised to minus 1, Kelvin raised to minus 1. So this is a unit to find out specific heat. This is the unit of specific heat capacity. Okay. So specific heat is defined as the amount of heat per unit mass absorbed or rejected by the substance to change its temperature by 1 unit. So here we are also specifying the change in temperature. The temperature change should also occur by a unit, 1 unit, and the mass of the substance also should be expressed in unit scale. Now, mathematically, specific heat capacity is 1 by M into delta Q by delta T. We had already discussed that. And the specific heat capacity depends upon the nature of substance and temperature. So that is written here. It depends on the nature of substance and temperature. The SI unit of specific heat capacity is joule, kilogram raised to minus 1, Kelvin raised to minus 1. Next is molar specific heat capacity. So what do you mean by molar specific heat capacity? It is the heat capacity per mole of the substance. Okay, and it is defined as the amount of heat absorbed or rejected by the substance to change its temperature by 1 unit. Okay, so it is the amount of heat required to increase the temperature of 1 mole of a substance. Not 1 unit of mass. It is the amount of heat required to increase the temperature of 1 mole of a substance by 1 unit. And this molar specific heat capacity is denoted by C. C is equal to S by mu, where mu is the number of moles. So the equation to find out molar specific heat capacity is C equal to 1 by mu into delta Q by delta T. Here also it depends on the nature of the substance and its temperature. The SI unit of molar specific heat capacity is joule per mole per Kelvin. That is joule, mole inverse, Kelvin inverse. Okay, so this is the SI unit of molar specific heat capacity. And there are 2 types of molar specific heat capacity. One is molar specific heat capacity at constant volume. This is molar specific heat capacity at constant volume and molar specific heat capacity at constant pressure, that is Cp. Okay, so this is about molar specific heat capacity. So we had discussed different types of heat capacity. First we discussed about heat capacity. Heat capacity is the amount of heat required to increase the temperature of hot substance. Then we discussed specific heat capacity. Specific heat capacity is the amount of heat required to increase the temperature of unit mass of substance by 1 unit. Then we discussed about molar specific heat capacity. It is the amount of heat required to increase the temperature of 1 mole of a substance by 1 unit. There are 2 types of molar specific heat capacity, that is molar specific capacity at constant volume and molar specific capacity at constant pressure. And one information I want to share with you, that is water has high specific heat capacity. That means if we want to heat water, large amount of heat is required. If we want to increase the temperature of water to a reasonable value, large amount of heat is required. It cannot be heated quickly. So water has high specific heat capacity. So it is used as coolant in automobile radiators and as a heater in hot water baths. And due to high specific heat capacity of water, land is more warmer than water during daytime. Okay, land, the specific heat capacity of land is less, so it gets quickly heated up during daytime. At the same time, due to the high specific heat capacity of water, it is not quickly heated up during daytime. Okay, so this is about the heat capacity and specific heat capacity. So we had already discussed about the molar specific heat capacity at constant pressure and constant volume. So if you want to define, how will you define this molar specific heat capacity? See, if the gas is held at constant pressure during the heat transfer, then the corresponding molar specific heat capacity is molar specific heat capacity at constant pressure. That means the heat capacity at constant pressure, that is molar specific heat capacity Cp. Then what is Cv? Yes, in this case volume of the gas is maintained constant. Okay. And water has the highest specific heat capacity, because of which it is used as coolant in automobile radiators and in hot water baths. We had already discussed that. Then calorimetry. Calorimetry is defined as heat transfers from a body, or heat transferred from the body at higher temperature to the body at lower temperature, provided there is no loss of heat to the atmosphere. So what is calorimetry? Calorimetry is defined as the heat transfer from a body at a higher temperature to a body at lower temperature, provided there is no loss of heat to the atmosphere. That means heat flows from hotter body to colder body without any loss of heat to the atmosphere. That is calorimetry. And what is the principle of calorimetry? Principle of calorimetry is the heat lost by one body is equal to heat gained by another body. Okay. Consider a container. It is filled with water. It is now a cold water. So we have dipped a hot body inside this cold water. So after some time we can see the temperature of both the objects have become equal. Okay, so what happened? The temperature lost by this hot body is gained by the temperature, or is gained by this cold body. So the temperature or the heat lost by this hot body is gained by this cold body. So the heat lost by this hot body is equal to heat gained by this cold body. So this is the principle behind calorimetry. And the device which measures calorimetry is known as calorimeter. Now this is the description of calorimeter. So calorimeter consists of a metallic vessel and a stirrer. Both are made of same material, copper or aluminium, and the vessel is kept in a wooden jacket so that there is no heat loss. Okay, so here you can see it consists of a metallic vessel, and that metallic vessel and one stirrer will be provided, and this metallic vessel and the stirrer are made of the same material, copper or aluminium, and the vessel is kept inside a wooden jacket, and this wooden jacket prevents the heat loss. A mercury thermometer can be inserted through a small opening in the outer jacket. So here you can see a thermometer. It is inserted through a small opening in the outer jacket. So this is the description of a calorimeter. So children, that's all for today's session. Notes of the topic and YouTube video have been uploaded. Please go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.